Okay, everyone. Assalamualaikum warahmatullahi wabarakatuh, and good day, everyone. I'm sorry to say that an apology for those viewers from my YouTube. Okay, I almost take some time to produce this video. So I received some comment when the viewers watch this video related to determining concentration of compound using GCMS. Okay, so the software that I've been used for this in this video is this one, which is we call it enhanced data analysis, yeah, or we call it this one coming from the Agilent software. But the one that I show you in this YouTube is using the quantitative method using the software. Okay. However, for today, I would like to address the comment from some of the viewers stating that how if they don't have the software, but they want to get the results and then quantitate the uh, samples. Okay. So allow me to share the software. So the one that I have here is this one. Okay. For example, before we quantitate, we have to establish a calibration curve. So let's open one standard. Yeah, this standard, the one that I have is 37 fatty acids, methyl ester. But the one that I want to focus is only one compound. Yes, for example, I open up one of the file with the concentration of 5,000 ppm. 5,000 ppm is not for the specific compound of this fatty acid, but it's the whole as uh, mixture of the compound that I have, the standard that I have. Okay, so for example, I open this file. So usually in the GCMS, you will get two type of data, which is the first one is mass spec data. Another one is SIM data. SIM data means selected ion monitoring. So if you click this one at the first place when you run the GCMS, you will get both of this data. So the first one in the top is the scan mode, yeah, which is they will the GCMS will collect as much as possible, including the background, including the any additional compound that they can get in the analysis regarding of any compound that they can get from the sample, yeah. And then for the sim data, they only collect those ion that you have, the ion mass that you have introduced or registered in the gas chromatography mass spectrometer at the first place before you run the sample. So you can see here, if I choose sim data, yeah, you will have or we will have 37 compound. Okay, so this one I can zoom. Okay, so actually there are 37 compound here. Okay, so for example, I would like to quantitate one compound at this one 10.1 something a minute, yeah. So this is actually belong to one compound which is named as this one hexanoic acid, yeah. This is the one, the paper that I have published, yeah, using the similar calibration curve and data. So at 10.144 minute, this is the hexanoic acid. So how we want to quantify sample in this containing this hexanoic acid. So at the first place, okay, let's unzoom first. Okay, we are looking at this compound, again, yeah. You need to integrate the GCMS result, yeah. So you have to go to click Chromatogram, select integrator, and then choose RTE integrator, and then click OK. Then you go to Chromatogram again and then click integrate. So you can see here at this minute 10.12 6 minute it is hexanoic acid, okay, which is we can say almost near to the one that I have been reported 10.144. Okay, so now in order for us to set up a calibration curve, yeah, we need to identify the area of this peak. Okay, you can see that is a line that integrate this peak, yeah, the red line to indicate the area. Okay, and then you can see that there's a blue color number, which is 10.126 minutes. So integration actually will recognize and introduce this retention time for the particular compound in our system. Okay, and then from here, we can identify the area. Okay, so to know how much the area for this 10.126 hexanoic acid, can go to the chromatogram and then click integration result. So you go to the retention time here, looking at 10.126. So this is here, okay? And then go directly to the right side. You can get the area here is 1418, okay? So for example here, 1418, you can open one Microsoft Excel, okay? So the Microsoft Excel has been open. So just type here, concentration. The unit is ppm, and then we want to know about the area. So the first standard is 5000 ppm. The area is here 1418. 1418. Okay, so just keep it this data first, and then let's go to another concentration, which is a higher concentration. Open up a new file. Okay, so at this number of file, we have the 5000 ppm. So I want to get the higher level, higher concentration, which is 10,000 ppm. So you just open it. Okay, so you have to do the similar one. Go to select to the signal and then choose sim data. Okay, so again, I would like to remember, I would like to remind everyone uh, why we choose sim data, because at the first place, in this study, I really want to focus on certain particular fatty acid methyl ester, which is I have already run 37 compounds. So instead of I just let the system to record it or to looking for other compound, I want the GCMS system to only focus to these 37 compounds only. So that's why I use the sim data, where I added or put in the setup of mass 102 until 343 for the whole 37 fatty acid methyl ester. So in this case, cyanoic acid, I put it 130. Okay, so that's why we get this one. So in order for us to identify again where is hexanoic acid, you can go to chromatogram, click integrate. So you can see here it slightly changes, at 10.112. So this is at 10,000 ppm. You can identify the area, go to chromatogram and then click integration result. 10.112. So the area is higher here, 3034. So you go to the Excel, 10,000 ppm, go back here, which is 3034. 3034. Okay, now move to the higher concentration. Just close here and then go to here, load data file again. I will choose the number 12. Okay, okay, so again choosing only the data sim. Okay, zooming here and there. Okay, go to chromatogram, integrate. So at 10.126 this time, go to integration result. 126 is 4817. So 4817. This time the concentration is 15,000. Here, 15,000. Okay. So you just have to proceed until we get other compounds. But never mind. Let's move. Okay, so I have continued until to 50,000 ppm, yeah, and then I have recorded at the area. Then you have to take note for those who proceed with method validation and verification, you have to at least have seven concentration, including the blank, yeah, for the uh, calibration curve. So in this case, for example, I want to add a blank, or I want to put the concentration as a 0. Okay, so you have to open the blank data. So in this case, I have this blank data and number 17, and then I have quantified this one. It's not quantified. I have integrate. Okay, and then if you can see, nothing has been integrated in here, meaning that there is no hexanoic acid being detected here. So you can confirm with the integration result. Yeah, at 10 something, yeah, minute 10.12 minute, there is nothing there. Okay, because the one that we have is at 9.6 and 15, so we can denote as the area will be 0. Okay, so from here in manual establishment of calibration curve, you can go to uh, draw the scatter plot. Okay, so you will see here we have the scatter plot, and then this is the chart title, hex sorry hexanoic acid, yeah, concentration, oh, calibration curve. Okay, so this one you can add the chart element axis title. No, we have to go to the label first. Yeah, this one, this is concentration, concentration, ppm, or we call it microgram per mil. And then we can also put a axis title here. This is area of the peak, or peak area. Okay, and then from here we can identify the r square. In order for us to introduce this one, we can go to have a trend line, choose more trend line. I would put ensure we click linear here, okay? And then click display equation on chart and display r squared value on chart, and then you can get here. So you can see the r squared that we have is r squared equal to 0.9954. This one is the we call it the equation of the calibration of the, or we call it linearity equation. So in this case, we have established a calibration curve here. Okay, okay. For example, I would like to put here calibration curve equation. Okay, so the one that we have is y equal to 0.3288 times x minus z 70.435. So you can see the x value is 0.3288. Yeah, the intercept is p, which is we know that uh, it is negative 0.70435. Okay, so you know that in order for us to have a calibration curve, the calibration curve equation equal to y equal to mx plus t. So this is the common calibration curve information. So yeah, let's put it here. Okay, so using this information, we can identify how much the concentration in the sample. Okay, for example, how about I open one data. Okay, for example, there is one data I can open here. Okay, so how about if we try to quantify one data? For example, I would like to have again for example, I choose this 10,000 ppm, yeah, of the fatty acid beta as the standard as unknown. Okay, actually unknown. We don't know how much is it. So we choose this one as a uh, we want to know what is the concentration. We assume this is a unknown sample. So we just go back to K, okay, and then go back to integrate, and then go back to integration results. Okay, we can get this 10.112 with this area, but this one is similar. Okay, however, how about I choose another sample? I would like to have this one. For example, for example, this is an sample containing I think this is a biscuit containing some fatty acids, yeah. And then I would like to integrate this one, and then you can see at the integration result, okay, at 10.126, this is the acyanoic acid retention time, we get the area of 309. Okay, so you can put here the area. Okay, sample area is again which one? This one is 309. Okay, 309 actually is very low, yeah, compared to this 5,000, but it's okay. We just want to know how to calculate this one. Okay, so for us to identify how much the concentration of the fatty acid, hexanoic acid in the biscuit, the sample is belong to a biscuit actually, yeah, whole biscuit, close. So we can use this formula by writing this way. Okay, so x equal to y minus c, yeah, y minus c divide by m. Okay, so this is the formula. So let's do it. Okay, put this formula, go to area. Okay, sample area, the y is here actually, 309 minus c is this intercept, and then divide by m. M is, oh sorry, m is this one. This is not m actually. Okay, so let's go to do this one. M is here. Okay, so the concentration that we can get is 941 ppm. Okay, so let me explain again. Okay, sample area is y. Okay, so from this equation, y equal to mx plus c. So the m is a slope 0.3288. Yeah, I'm sorry for the wrong information. Yeah, the c is the intercept, which is in this case is negative 70455. It goes here, yeah, intercept, and then sample area is y actually. So in this case, when we try to identify the area of hexanoic acid in this biscuit sample, we can get at 10.126 minute, the area is 309. So we go back to put here 309. And then from here, by using this formula, x equal to y minus c divided by m, we can get the concentration of hexanoic acid in this biscuit. Yeah, in this biscuit is 941.9232 ppm. Okay, so I think that's all from me. This is for those who are asking about how to do a quantification and establish a manual calibration curve using this GCMS data. Okay, so what do you need at the first place is you need to know the retention time of your particular compound, and then you need to know the area. Yeah, area for those for both calibration standards, yeah, and then for the sample as well. So from by using this area and the retention time, you can identify the concentration of one particular compound in the sample. I think that's all from me. Oh, by the way, this also apply for HPLC analysis. You can carry out the similar uh, approach to identify any compound using a HPLC, because HPLC also produce a peak, and from that peak you can get the area. Okay, that's all from me. See you again in the next video. Okay, sorry for the delay of the publication of this video. See you again, guys. If you think this is really beneficial, please subscribe again to this channel. Thank you. Assalamualaikum warahmatullahi wabarakatuh.